numerator is all the S or C functions are turned into D. So let's collect the terms. So outside of this sum, we have 1 over 2m-ary blah, plus 1 over 2m-ary blah. So that's 2 times 1 over 2m-ary d over 2 root 2 sigma squared. And inside the sum, what do we have? We have 1 over 2m outside the sum already. For one thing, this and that are the same. So it's RC of this plus RC of that, which is 2 RC d over 2 root 2 sigma squared. How many? The other thing to notice here is that this is no longer dependent on I. So I'm summing over constants. So I get, how many terms are there here?
M minus 1.
Or m minus 2.
Sorry.
From 1 to m minus 2, so there's m minus 2. So we have, there's 2 of these, so that's 2 times m minus 2 per c d over 2 sigma squared. So again, we can collect the terms. So we have, I'll let this 2 cancel with this 2 cancel with this 2, and we get 1 over m over c d over 2 sigma squared plus m minus 2 over m over c d 2 root 2 sigma squared. Okay, 1 over m plus m minus 2 over m. So in other words, m minus 2 plus 1 over m is equal to m minus 1 over m over c d over 2 root 2 sigma squared. Okay, so if what were the assumptions leading up to this? The assumptions leading up to this were that every point was equally probable. Every threshold was halfway in between the noise-free filter outputs, and all of the noise-free filter outputs were equally spaced. And if that is all true, then this is your probability of error. That's the probability of symbol error. That's the probability of confusing any two symbols. So that actually looks kind of familiar. So let's set what if m equals 2? In other words, binary. Well, what were the assumptions leading up to? So we had an expression leading up to when we were talking about the match filter. Over here, we haven't talked about the match filter yet. So leading up to the match filter, we had the following expression of probability of error. We had 1/2 C, and here we had S0 is equal, excuse me, S1 is equal to alpha S0 in binary. And we had the probability of error in that case, 1/2 C, 1 minus alpha S0 divided by 2 root 2 sigma squared. So let's substitute, let's see if everything over here holds over here. So let's think about the assumptions. Okay, firstly, equiprobable. Yeah, in order to get that, we required equiprobable bits. That was one of the assumptions we made leading up to the match filter. Equally spaced noise-free filter outputs. So there's only two, S0 and S1. So by definition, they have to be equally spaced because there's only one of them. Third one is threshold halfway in between. We had already showed by that point that the optimal threshold is halfway in between those 2 points, so that's true. So the binary case appears to satisfy all of the modeling assumptions from over here. So let's substitute in some values. If m is equal to 2, then d is equal to what? What's the distance between these two? So S0 is just S0, and S1 is equal to alpha S0. So d is what?
1 minus alpha.
Yeah, it's S0 minus alpha S0, which is 1 minus alpha S0. So if we substitute in everything here, in the binary case, we get 2 minus 1, which is 1, divided by 2, curve C, 1 minus alpha S0, which is D, divided by 2 root 2 sigma squared. So this generalizes the binary probability of error expression. Any questions on that? Okay, something else we touched upon last time. This is the probability of confusing any two symbols. So in other words, any one of the m symbols that we send, this is the probability of confusing any two of them. If we assemble in this case, probability of error is the probability of symbol error. So let's let p sub bit error be the probability of bit error under whatever. So this is only relevant if you have a mapping from symbols to bits. So what do we have? We have a mapping from symbols to bits. That's like, I showed you an example a couple of classes ago. For instance, we could go from binary to 4-ary by grouping pairs. We could go from binary to 8-ary by grouping triples. Similarly, you can go from binary to n-ary by grouping n tuples of bits. So if you make an error in a symbol, what's the probability of bit error? Unfortunately, this depends on the mapping, and it's not an easy arrangement, so it's usually not available in closed form.